so far we have had really a series of wonderful, excellent presentations that has given us a lot of food for thought for discussion in the afternoon. There are 4 sessions in the afternoon, each about 40 minutes long, so we will have a lot of time to develop these ideas further. What I wanted to do now, we have heard from Professor Joshi on how successful a university-industry collaboration can be in the Indian context. And we need to address how we can adopt that to the US context. And then we heard from Randy Roberts about what are the grand challenges from an industrial perspective, how to couple, for example, the fluid mechanics with the chemistry and deposition problems with asphaltene, with gas hydrates, etc. And we finally heard from Professor Sangani about very exciting kind of research that is being done, supported at NSF. There is, after all, National Science Foundation, so the focus is on science. And I guess in India you would call it as Department of Science and Technology that funds these. So there's already a recognition that technology is an important department there. And also for historical reasons, I think the collaboration between industry and university is much well respected and received in India than it is here. So our goal is to see whether we can learn from that experience and organize ourselves in a way that we can also achieve some advances. So what I'm going to do in the next 20 minutes or so, I'll try to cut it down as fast as I can. Give you my idea of, I should say not mine, our idea. There are 4 of us that started talking about it 2 years ago, and how we want to structure ourselves. And so I'm going to sow some seeds for discussion in the afternoon. So as a chemical engineer, let me just begin by saying, what are the things that we do? Okay, we basically separate things that are mixed, we mix things that are separated, we change things from one to the other form. Essentially, we take raw materials and convert them into useful products so that we never like them in their natural state. We want to change their state so that it is more useful to us using a variety of processes. Okay, I've identified several of them here. And if you look at the history of how chemical engineering evolved from industrial chemistry, you will see that in the early 1900s, the training of students was through apprenticeship in a particular industry. Okay, so if you're going to be working in sulfuric acid industry, as a chemist, you learn about the chemistry and you go to the industry and practice. And similarly, you go to ammonia plant, you go to nitric acid plant, whatever it is. And there was really no intercommunication. But the thing I'm trying to point out is every level of intercommunication increases our level of understanding and improves the technology in a continuous fashion. So the first level of course, synthesis occurred through this unit operations, where we recognize that the same units are being used in all these plants, but one person does not know how it is used in the other plant. So the course 10 in MIT and I think in Imperial College in England, chemical engineering had its birth there, where we began to see the unity in these operations, and unit operations became a major topic. The second major involvement occurred in the 1950s when we saw the unity in the mathematics describing these processes. So the mathematical modeling essentially became the uniting frontier in terms of trying to understand, for example, whether it is distillation, absorption, extraction, the underlying models are very similar to it in terms of mathematics. So I think that revolutions were created by Birch-Stever and Lightfoot. We all understand that. And then the next revolution is use of computers, introduction of computers to solve these mathematical equations, no matter how complicated they are. Computers enable us. And so the process simulators, Aspen HYSYS, and more recently, ANSYS FLUENT. There are a number of other products that are synthesizing these. So they give us a very powerful tool in our hand. Similarly, on the experimental side, very powerful tools have been developed. So this is a slide I put together, I guess, 2 years ago when I was writing the proposal for IGERT. My point is, if you look at the automotive industry, Model T versus the modern Porsche, there has been a tremendous progress, but it has been achieved not by a radical overnight change, but by sustained improvement, gradual improvement over a period of 60, 70, 80 years. And they have embraced these modern tools much more widely than what chemical industry has done, I think. And the same thing with the aerospace industry, from Wright brothers to a modern Dreamliner, even though it has been grounded now, it still has very significant accomplishment, I think. But if you look at the chemical industry, 1940s picture from the internet and the 2000 picture from the internet, the internals really haven't changed much. Okay? There are innovations that are being brought by Professor Joshi and a few others around the world, but essentially if a plant works well, we don't tinker with it. Okay? So we are happy with it. It may be over-designed, but it produces. So why bother about it? Okay? So that attitude has to change, and I think Professor Joshi's work is showing that there are enormous benefits to be gained by changing that attitude at all levels, for industry, for universities in terms of education, and asking more fundamental questions, training the students using advanced experimental tools, advanced computational tools, and more deeper theoretical understanding. So I'm going to show you one example, and I have several examples. This one is a picture taken from Fractionation Research Incorporated, which shows how complicated the multiphase flow is. I guess I don't need to show this because we've already seen several presentations that talked about how complicated multiphase flow is. What is this? This is a picture of a gas liquid transfer inside a single distillation tray. Okay? So as you increase the vapor flow rate, you will find that at very low flow rates, the liquid drips from the top part. We call it as the leaping region. And when there is good intermixing between the vapor and the liquid rate, you have this froth regime. That is the ideal regime that you would like to operate so that there is good mixing and good transfer of the species, good separation. But in this case, the velocity is so high that the droplets are actually carried to the upper tray, and again mixing occurs. We want to separate. Okay? So the way that we understand this process is actually doing these experiments and documenting and dividing the flow map into various regimes of operation. Multiphase flow is very complicated, and Bachelor's quotation, divide and conquer, has been used essentially. So you isolate each flow regime and you try to understand, develop empirical correlation models for understanding and designing in each one of those regimes. But if you look at a single tray, it can be as large as 15 feet, 20 feet in diameter. Okay? The governing equations to understand the dynamics are all captured in this equation. It's nothing but Newton's law of motion applied to fluid mechanics. And in principle, all the secrets are hidden in there. Okay? For single phase flow or multi-phase flow, one can argue that. So the question is, how do we get the information that is hidden in there? Because there are nonlinearities in the problem, and there are challenges in solving those nonlinearities. We are overcoming one by one. In terms of our computational algorithms, advancement in those, and validation is an important part because we make a lot of approximations. And I'm going to take you through some of those arguments in terms of where are the uncertainties in the modeling as we apply it to industrial scale problems. Okay? Historically, this is how we have designed distillation column. I'm just focusing distillation column as an example. Okay? So in the 1920s, we developed methods for design of distillation column, making a lot of simplifying assumptions because the process is so complicated. So we just assume constant molar overflow, well-mixed stage, and there is a design procedure which is still taught, which is a great technique for teaching what happens and what is the impact of changing operating conditions on the performance. But if you actually design it and say compare it with the actual plant, it will never match. The number of stages that you design will not match with what you actually find. So what are the reasons for the mismatch? The reasons, of course, are the assumptions that we made. Now, in the 80s, when Aspen and ISIS came, we were able to relax this assumption. Constant molar overflow is no longer needed. We can put rigorous equations to track changes in the vapor flow rate. But we still assume that the flow and the velocities, the compositions are uniform at every point across the string. Okay? So that is not going to be valid. That's an assumption that we made, and that's not going to be valid because of large-scale heterogeneities that develop inside such process vessels, which I think has been pointed out already. So our focus should be on trying to identify and understand the causes for these large-scale heterogeneities in those vessels. And if we can do that, we can make significant process. As Randy pointed out, the errors could be 100%. If we can reduce it to 10%, we are making great progress in terms of making the reliability of these models much more accurate. So this is one of the master's thesis a student of mine did some time ago. Basically, it's a CFD simulation, a two-phase simulation of a single tray. What happens to the dynamics? And what you see is, of course, produce colorful pictures like this, which tell you what are the phase distributions inside such a vessel. But really, these are qualitative pictures at various flow conditions. What we really want is a quantitative validation. Again, a point that Professor Joshi talked about so elegantly. And well, this is again a picture that gives us an idea of where the streamlines are, where the path lines are. But in order to validate quantitatively, what this student did was take some experimental data that was published in the literature, where they measured what is the velocity variation across the tray. Okay? So we took that, and these are the experimental data points, and these are the simulation results. So we can capture roughly the tendencies in the large-scale heterogeneities. We don't assume that it is a flood flow that goes from one side to the other side, or it's a well-mixed stage. So that's one example of how progressively CFD can help us shed greater light into the operation of these process problems. As I was listening to Professor Joshi this morning, I was just thinking myself, I have also worked on a number of problems, but I have not taken the last 3 steps. I have stopped at the first 4 steps. That is, I understand the problem, I develop the model, I do the validation, but I don't carry it to the next step, which is actual design and actual improvement and optimization. Okay? And that is what has been missing in my career. So the next 10 years or so, I would love to focus on that, but I need industrial context for carrying the last step. So we have worked on a number of such projects. I think that I list here. Gulf of Mexico oil spill is something that we are working on. Heavy oil and with sand and water. A lot of my work in the early years in Alberta was supported by oil sands industry. Okay, so a lot of these projects actually relate to oil sands recovery. Progressive cavity pumps, gravity separation vessels, fluidized bed reactors, crude distillation towers, etc. Erosion, corrosion, that's a major problem as well. So I'll take a few minutes to talk about our plans for integrated research on multi-phase process model development. So our vision basically is to understand industrial scale applications. So we are focusing on understanding industrial scale transport phenomena, fluid mechanics, heat transfer, mass transfer, with the heterogeneous distributions that spontaneously develop in multi-phase flow situations. How do we understand that? And the problem can be multi-phase reactors, turbulent and non-Newtonian flows. It could be flow in the wellbore. So there are a lot of situations where multi-phase flow occurs. And that's why the 4 of us have come together to pool our expertise and then participate in the process of training the next generation of graduate students while engaging in industrially relevant research, but maybe carrying the last step also in terms of improving the actual design. To advance the fundamental understanding and modeling of multi-phase processes, that's one of the things that we want to achieve, and to provide economic benefits of improved process efficiencies. And this is something I think to change the design paradigm, which comes from Professor Joshi's presentation. How do we step back if there is a problem that an industry is facing with a particular equipment? How do we step back, take a look at the overall picture, start from understanding the basics of transport phenomena, and then come up with a solution that is taking a holistic picture of what happens in the reactor, not just a patchwork of if I do this, I can overcome this problem. Okay, so that's something that I'm learning from working with him. And of course, we have a number of models that we are involved in developing, the two-fluid model, the discrete particle modeling, and the direct numerical simulation, etc., coupled with the experimental techniques, advanced experimental techniques. The mission, I guess, is to engage the Louisiana industry to help realize the benefits of using advanced computational and experimental tools. So one of the ideas is, and this is, I'm showing the ideas for discussion this afternoon, maybe start a multi-phase consortium that will engage in pre-competitive research that all industries could see a benefit. And we will engage in research that could potentially be applicable to the industry in here. And the other one is to workforce development. That is, our main job, primary mission is to educate the next generation of engineers. To find internship opportunities, this I think is an important one to engage with industry. We want to place our graduate students in the industry for 3 months, 6 months, so that they can learn one of the things, I guess, chemical engineering education, the way that it has evolved is, in the early 30s, the industrial chemistry era, you will actually learn about various process flow sheets. How is sulfuric acid made? How is nitric acid made, etc. From a book called Shreve. But nowadays, in chemical engineering curriculum, you don't see that. Okay, it's A going to B, and there is a mathematical model underlying it. There is a numerical model underlying it. So the students miss that link. Okay, even though they are very trained in terms of the most advanced experimental and computational techniques, until they go and sit in the plant, okay, this is how polyethylene is produced. This is how PVC is produced, for example. So that opportunity we should provide for the graduate students. So that's one of the things that we would like to include in the cluster, one of the activities that we would like to include. The other one is maybe organize a weekly seminar on multiphase flow using technology. So I'm envisioning, for example, inviting 4 international speakers, like Professor Joshi, for example, in a year, maybe 8 national speakers from various national labs and academic setting, and 30 to 40 industrial presentations. That's what I want. I want to hear from people in industry. So these seminars will be broadcast from LSU, but if we have a cluster that is spread across in many places, we will have that transmitted and recorded. And then offer short courses to industry. So these are some of the things that we think we might be engaged in. If there are other ideas, we would like to hear from them. This is a map that I put together when I was working on the IU proposal. And it basically tells you how we can integrate the expertise that occurs in that is available in an university setting to solve multiphase flow related problem. So it focuses on 2 central areas, the multiphase modeling and multiphase experiments, advanced multiphase experiments. So among the 4 of us, myself and Mayank are more on the computational side, and Vadim and Dimitris are on the experimental side. Vadim has a wonderful $3-4 million pilot plant he will talk about, and Dimitris has some of the most advanced laser diagnostic tools and stuff like that. So this would be the core, but to advance, what we need is actually problems from industry and graduate students. We will mix them up. So we'll put them through internship, for example, get some experience, and using process diagnostics, we'll try to identify what are the units that may be not functioning properly, and so there's opportunity for inquiry into that. And process modeling, using ASM type of model, what is the benchmark? Is it performing up to the benchmark? And basically, at this stage, we started a detailed investigation of specific examples, like Professor Joshi talked about. Okay, and we may need support of people from computing science for developing advanced computational algorithms. We will need expertise from experimentalists using AFM and stuff like that to characterize the interfacial phenomena, for example. Okay, so bring all these together, build a model, and then we can start taking the final step of process identification, process design, process improvement. And of course, if we have such models, maybe using reduced order models, we can then do process optimization and process control also on models that are derived from physics-based principles. So this is the 4 of us. You see the picture, but you will see them also present very shortly. And this is the idea of that cluster. Okay, so we are trying to work on a cluster at LSU, chemical, mechanical, petroleum engineering, but we are open to memberships from other departments as we grow. And I've been talking to Petroleum Institute in Abu Dhabi, where I work, and there are great opportunities there too, because this is funded by Abu Dhabi National Oil Company, and they have refineries, they have gas plants, they have polyethylene plants, etc. So there are opportunities for implementing a model like that in such a place, and they are also a great test case because their research is very nascent. They are just starting right now. They don't have a research culture at all, but they are interested in starting a PhD program. So there are opportunities for exchange of PhD students and faculty between such institutes. The cluster concept will inform other universities as well. Okay, so I have already, through my experience at the University of Alberta and the Homi Bhabha Institute that Professor Joshi belongs to, we have exchange of students between these institutions. I need to develop interactions with the University of Florida, University of Houston. There are faculty members working in these places, Jennifer in Florida and Bala in University of Houston, for example. So we could potentially expand this kind of academic environment where similar research takes place at different locations, but we all participate on a single goal of increasing the university-industry interaction. How am I wasting time? I think you need to control my time, man. I cannot control my own time. Oh my God, I'm behind. So let me just quickly go through some of the more expertise that I have. This was supposed to be the last part of my talk. So we've been working, I believe that the two-fluid model is going to be the practical one in terms of computational efficiency when we want to apply this to industrial scale problems. But the higher level fidelity is the discrete particle modeling, which we have also developed some algorithms for. And the highest level of fidelity will be the direct numerical simulation, where we track the complete interaction between the particles without any simple thing, averaging approximations. So as I said earlier, all the secrets for fluid mechanics is governed in this, and this is a famous quotation that I love so much. In every talk that I give, I have to put this one. It's a quotation from Feynman, one of the greatest minds that I ever learned, about G.A. Taylor, another greatest mind in fluid mechanics. And this is taken from the book by Feynman. It basically says that the main lesson to be learned from Taylor's work is that tremendous variety of behavior is hidden in the Navier-Stokes equation. All of the solutions are for the same equations, only with different values of rotational speed. We have no reason to think that there are any terms missing in these equations. These equations are complete in that sense, as long as you have incompressible Navier-Stokes, the incompressible fluid. So the only difficulty is that we do not have the mathematical power today to analyze them. That we have written down the equation does not remove from the flow of fluids its charm or mystery or surprise. So that challenge still remains. This was written in the 60s, so computational fluid dynamics has advanced quite a bit, experimental fluid dynamics has advanced quite a bit, as Professor Joshi illustrated. So we have reason to believe that we can use these to develop better understanding. Let me just go into the multi-phase flow problem. And these are the equations, the time averaged equations for turbulent flow, which introduces a need for certain closure relationships in terms of the turbulent interaction, Reynolds stress term and Reynolds flux term. Okay, but if you talk about the multi-phase flow, what happens is, imagine that these are oil droplets in water. Okay, so when we are doing the averaging, it gives you a conceptual picture of what happens. How do we lose the information? So when I'm averaging this, I'm basically losing the information about the edges if my averaging size is very small. Okay? But as I increase the averaging size, you will find that I progressively lose information. But what I'm interested in from a practical point of view is that to be able to identify that a certain region of the equipment has a higher concentration of a certain phase than the others, large-scale structures. I'm not interested in predicting where every droplet is, because that is an impossible task. There are billions of particles, billions of bubbles, etc. Okay? So the two-fluid model allows us to answer questions on that scale. We lose information, but we need to provide closure information for that. And this is the process by which we get the average models, and this is the information that we lose. What is the interaction between the two phases? Direct numerical simulation will allow us to actually calculate that, because we resolve all the stresses on the surfaces, so we can calculate what the force is. So that is the highest fidelity in terms of the multi-phase models. But in the average models, we need to provide a closure relationship. So one of the research questions would be, can we develop scale invariant closure relationships that will work from laboratory scale to the field scale, through the pilot scale? If we can do that, we can cut down on the number of pilot scale experiments. We can use that to innovate and intensify the processes. So this is the volume average equation that you will find typically in today's simulators. And these are examples of the interaction terms that are typically used. And this is the discrete particle modeling framework, which says that I'm still going to treat the continuous phase, liquid or gas, in the volume average sense, but the high fidelity comes from the fact that I'm going to track the impact of each of these particles very rigorously. Okay? And there are a couple of variations on this, time-driven and event-driven. In the DNS, what we do is we completely resolve. So there is an equation for the fluid phase, and there is a rigid body dynamic equation for the solid phase, and they can interact with each other. And these algorithms have been developed for the last 15 years or so, and we have been also working in this area, developing some of these algorithms and codes. And the same thing applies for two fluids. When these two are immiscible fluids, you have the equation for fluid domain 1 and equation for fluid domain 2, and the coupling term, and they are tracked rigorously. Okay? So that is the range of models that are available at our disposal. And this one basically shows you how the various models are interrelated. Randy talked about multi-scale. Okay, so what we are doing currently is, if you have a chemical process unit, I take the data from the pilot scale, get the large scale heat transfer coefficient, mass transfer coefficient, etc., and design, making mass balances over the equipment scale. But what we are arguing is, in order to do that, we need to input to that overall heat and mass transfer coefficient, K efficiency, resonance time distribution, obtained somehow from experiments. But if we can examine processes at this scale, the volume average scale, we will get a better idea of the phase distribution. But in order to do that, we still need to input drag and lift forces, interface heat and mass transfer, to close the relationship that I talked about. In the hierarchy of these models, if I go down one more level, by solving direct numerical simulation, for example, I'll be able to predict these things instead of getting it from experiment. Okay, but if you go one more level down, as Randy pointed out, you do molecular dynamic simulation, you can predict the properties that we need, for example, for the Navier-Stokes equation, the density, viscosity, surface tension, etc. But of course, even molecular dynamic simulation will need some input, which coming from intermolecular potential. So there is this whole hierarchy of modeling that are available at our disposal to look at these multi-phase processes in great detail. I think I've taken a lot of time, so maybe I will stop with that. These are the various kinds of problems that we have talked about, we have worked on in the past. The lessons learned from these studies: there are large-scale heterogeneous distributions that we need to pay attention to inside the process vessels, and the concept of interpenetrating continua is practical and adequate as long as we can get closure relationships, either from experiments or from direct numerical simulation. So I think I will stop with that, and maybe in the interest of time, I will defer the discussion to in the afternoon and ask